so you gotta say everything you can to get it.
Oh,
yeah.
Okay. Let's get going. Alright, so everybody needs to fire up their laptop, open up our studio, and do these steps. So we pretty much need to do this every week. Click over here to get the project for this class, 5065. So click on the project. It'll kind of restart itself. Then you want to click on the Get tab over here in the top right. So project, Get tab. Then you want to click on the blue arrow to download the material that we'll need for this week. So click on blue arrow. Mine says it's already up to date. Yours will download another file and it'll create a week 03 directory. And then final thing we want to do is session, set working directory, choose directory, and then click on week 03 so that your R session is in the week 03 directory. Yes?
Should we only have a bowling file? Okay.
I'll push the QMD file after class today. But you should also have gotten the recitation thing from week 2 Apruva did yesterday. So does everybody manage to open our studio, open the projects for this class, click the blue arrow to download the material, and change your working directory to week 03?
The internet is failing me.
Oh. Not a whole lot I can do about that.
What's the working directory?
Session,
For this?
set working directory, choose directory, and then it'll pop up something like this, and click on week 3. So the Columbia internet is, the Wi-Fi is not working?
Yes, and the edge reverse.
Okay. Can somebody hotspot?
I think I'll connect eventually. It's still like buffering, but yeah.
Okay.
That happened to me the other day. I just reset my computer and it worked.
Or what if you just turn the Wi-Fi off and back on?
It sounds too good to be true, but I
It
just
sometimes
I
works.
did all the steps and set the directory.
I did the classic turn it off, turn it back
Oh
on.
no, nothing's supposed to open, but it downloaded.
First thing,
Oh.
It's in the week 03 folder. There's a full link on our file.
How do I open it?
Oh, well, if you wanted to, you could click on File,
And then I
bowling like that. But you don't need to, but you could.
Sorry, you can still get 3 hours.
I'm sorry, I didn't read
Can you
it.
run through from the beginning again?
Okay, one more time,
Yeah.
because we need to do this every week. All right, I'm gonna close my project and run it from the beginning. Open your RStudio, click over here on Project, and then find the one for this class, 5065. Click on that. It'll restart. Now you're ready. And the Get tab in the top right here, click the blue arrow to download from GitHub the material we'll need for this week. I already have all my material. And then it should have downloaded some stuff for you. Last step, session, set working directory, choose directory, and then click on week 03. Okay?
But how do we know it works? It doesn't do anything?
Not really. It'll
So
pop.
what's the point?
Yeah, it'll pop up this in your console. Set working directory to week 03. That's the only indication.
So what's it doing?
Well, it downloaded the file that we're going to need in a second. But you don't need to play with it or anything. Okay. So is everybody on the same page there? All right. Oh, except I lost my. Okay. Okay. So this week we're going to talk about discrete probability distributions after we talk about the fact that we have already talked about before, but we have to talk about it every week. Read that. Do whatever you want with it. Okay, so just to review a little bit from last week, we started off by defining the probability of knocking down x out of n pins in bowling with this function involving the logarithm to base n plus 2 evaluated at 1 plus 1 over n plus 1 minus x. And we use those probabilities to simulate our frames of bowling, where the frames are independent of each other because that's how the rules of bowling say, but the two rolls within the same frame are not independent of each other because the probability of knocking down x pins on the second roll of a frame of bowling depends on how many pins are available upright to be knocked down. So knocking down 4 pins on the second frame, if 8 pins are available to be knocked down, is different from the probability of knocking down 4 pins on the second roll if 6 pins are available to be knocked down, etc. And we calculated many other probabilities that were implied by our simulations using dplyr syntax, but also we used the rules of probability, what I've been referring to as ancient calculations. In ancient times, they would have done this with a pen. You can do it on a computer, but it's still deterministic, more or less exact calculations, as opposed to the things with simulations, which are going to have some noise in it. But if you do a truly large number of frames, then the noise due to simulations is negligible, and you get essentially the same calculations as you would from ancient techniques when the ancient techniques are feasible. And this week, they're going to continue to be feasible, but like I've been saying, we'll soon get into situations in which the ancient calculations are unfeasible, but the simulation-based modern calculations remain feasible and totally, adequate for what we're trying to do. Okay, so let's go over some of the rules of probability that we learned last time. So, what rules are important for probability? Anisha.
Should add up to 1.
Probability should add up to 1 over the entire sample space omega. Yeah?
And therefore, the probability of each possible outcome has to be between 0 and 1 inclusive.
Right. Certainly, they need to be non-negative, and if they're going to add up to 1, then each of them needs to be less than or equal to 1. Okay, those are two of the more basic rules about probability. What other rules of probability did we learn last week?
Where 2 or more events are dependent, we multiply all them. So in this case, we would assume each roll or each frame is independent from the last.
Right. So the case of independence, multiply 2 probabilities together. That was a special case of what more general rule when events are not independent?
You add them. You add the 2.
No.
Can you repeat the question?
Yeah, so the idea of multiplying 2 probabilities together when they're independent is a special case of a more general rule that we learned last week, has general in the title of it. Involves multiplication. And it's a rule.
But the probability of A given B equals to the probability of A given B times and then normalized by probability of B over probability of A. Is that what you're referring to?
No, but that is the implication of what I was referring to. Anybody? Any general rule involving multiplication?
Was it joint probabilities?
Yes. How do we obtain the joint probability in general?
So the probability of A equals the probability of A times, or probability of A times B is probability of A times B given A.
Yes.
In the normal signs, and that's why it's more general rule because if they're independent.
Right. You take the first probability and multiply by the conditional probability of the second thing given the first thing. And that works even if the two things are not independent of each other. But you have to multiply an initial probability by a conditional probability. And that, as I was trying to hint at, is what is known as the general multiplication rule. Okay? There's one other rule, basically, that we learned the last time for dealing with probabilities. It's very important.
Probability of I don't know, A union B equals to probability of A plus probability of B minus probability of A intersect B.
Yes, that's correct. There's a little bit of math notation to just say that in words. Probability of A or B happening is the probability of A happening plus the probability of B happening minus the probability that they both happen, to correct for the fact you double counted the probability that they could both happen when you added the first two. Right? So that is the general addition rule. It involves the general multiplication rule because you have to subtract off the probability of both happening, but it has its own name, right?
They're mutually exclusive. It becomes just probability of A plus probability of B.
Right, so that's another special case of the extraordinarily general addition rule. If A and B are mutually exclusive, to which another word is disjoint, then the probability of A and B both happening is 0. And so you can subtract 0 or you can not subtract 0. Either way, you're going to get the same number. Then, of course, we have Bayes' rule, but Bayes' rule is a rather trivial consequence of the general multiplication rule, because the probability of A and B both happening can either be written as the probability of A times the probability of B given A, or it can also equivalently be written as the probability of B times the conditional probability of A given B. Since both of those are true, both of those are equal to the same thing, we can combine them in one equation, divide both sides by marginal probability, and we could end up with something like the probability of A given B is equal to the probability of A times the conditional probability of B given A divided by the marginal or marginalized probability of B, and that is Bayes' rule.
So would the numerator just basically be like the joint probability of A, essentially?
Well, joint probability of A and B.
Oh, and B, okay.
Right, and then divide by the thing that you want. Divide by the marginal probability of the event you want to condition on. That's B. Then you put probability of B in the denominator. And how do we obtain the what's the way in which we obtain the probability of B?
Law of total probability.
Which it
Which
requires
is,
us to do what?
you would do like the probability of like B given A times probability of A, and then you would do like it for the various like combinations, like depending on how many variables you have. So like B like not given A times probability of like not given A, or
And then once you do all that, then the last thing you do to obtain the probability of B is you have all those joint probabilities where the event B is involving the event B. What do you do to combine them into one number for the denominator? So like the thing we did last time, what's the probability of getting 9 pins knocked down on the second roll of a frame of bowling? How did we do that?
You sum it all up.
Right. you add the probability of 0 on the first roll and 9 on the second to 1 on the first roll and 9 on the second. Those two joint probabilities you add together to get the probability of 9 on the second roll. If B is, 9 on the second roll, then and you add those two. So to get the denominator of Bayes' rule, we have to invoke the general addition rule. Special case, those are mutually exclusive, but we still have to add stuff in order to obtain the probability of B in the denominator. Okay, pretty good. Pretty good. And then we use Bayes' rule to calculate the probability. X1 is 8, given that X2 is 2. Using Bayes' rule, but that wasn't really Bayesian, since there were no unobservables. And that's where things start to get controversial. If we want to do Bayes' rule for parameters, like beta in a regression, we can use the same mechanics, but we're going to get a lot of criticism from Ghost of Fisher. And maybe some other people, but mostly Ghost of Fisher. All right.
And Woolridge.
Question?
And Woolridge.
Yeah, Woolridge, he didn't really care enough to. Maybe he doesn't care to mention Bayesian once in a 900-page book. I don't think he's gonna troll you on Twitter or whatever because you took a Bayesian class. Fisher might. Questions? Okay. So now in your R console, if you do sourcebowling.r, it will load in the things that we did last week. So this is how you can tell that the stuff that we did at the beginning should work. It should create at least 4 things. PR, which was the function we defined to evaluate this probability here. Omega, which is the set of integers between 0 and 10 inclusive. Joint PR, which was that 11 by 11 table, and the elements of it had the joint probability of knocking down this many pins on the first row and this many pins on the first roll and this many pins on the second roll with the column index, so that their intersection gave you the joint probability. And then frames is like 10 million simulated frames of bowling. All right? So that's all what we did last week. Everybody's sourcebowling.r work? You got these few things? Okay. So goals for this week, we want to start learning about the main characteristics of probability distributions. And we want to learn 3 core discrete probability distributions, Bernoulli, binomial, and Poisson. Those have parameters in them. So we want to talk about what that means. Then we're going to add an unknown parameter to our bowling model, and then apply Bayes' rule in the context of bowling to update our beliefs about this unknown parameter given some data and a prior probability distribution. So we want to actually learn how to use Bayes' rule the Bayesian way. All right. So to start with, this is what we did last week. If you just call PR of omega, it will yield you these 11 probabilities for the events that could happen on the first roll of a frame of bowling. And then the question we need to get clear to ourselves, what is the mode, what is the median, and what is the expectation for the random variable that is the number of pins knocked down on the first roll of a frame of bowling, if these are our probabilities. So let's start with the first one. What is the mode?
Most commonly occurring outcome.
Yes, that's correct definition, which in this case would be
10.
10.
There's more generally, is it just the max of your probability mass function?
Or the argmax.
Or,
Yeah. So the element of omega that has the highest probability, assuming that to be unique. Which in this case it is. 10 is the mode for this probability distribution for the number of pins knocked down on the first roll of a frame of bowling. So that's good. Another thing to keep in mind is the mode is not very important for Bayesian. It's not a very important concept for Bayesian analysis. It's a much more important concept for frequentist analysis. But you should know what it is either way. Okay, question 2. What is the median for the number of pins knocked down in the first roll of a frame of bowling if these are the probabilities underlying that? Huh?
It would just be the sum of the probabilities of 4 and 5 divided by 2.
No.
Wouldn't it be 8?
Would it be 8?
7 and 8.
7 and 8?
Somewhere between them.
Somewhere between there?
However, the point you get 0.5 cumulative probability, whichever number that is.
Okay, so we've landed on the definition. Median can actually be defined a number of different ways, but this is how we're going to define it, is the most common in this situation. And I believe that's what we're getting at over here. Median is the smallest element of omega such that at least half the cumulative probability is less than or equal to that element, and consequently at most half is strictly greater than that element. And so, among other things, one was said was 8. So if we add up all these probabilities, that's going to be slightly more than 0.5, which you can tell a little bit easier by adding like 0.28 and 0.16, so that would be 0.44. If you added on another 11.5 to that, that would be too much. So 8 in this case is the median. The probability of less than or equal to 8 is slightly greater than 0.5, and the probability that it is greater than 8 is about 0.44. So 8 is the median, the smallest element of omega, such that at least half is less than or equal, and at most half is greater. All right. So clearly the median and the mode are different concepts, and in this case they're different numbers. 10 was the mode, 8 is the median. But since the median is defined as the smallest element of a sample space, such that, blah, blah, blah condition, it's going to be exactly an element of the sample space. So in this case, omega consists of integers, and so the median or the population median is also going to be an integer as opposed to something between 7 and 8. However, the estimator of a median from data will often take the average if there's 2 categories that have the same number of data points. But that's an estimator of a median as opposed to the definition of a median. Okay? Clear on that one?
In this case, it would be 8.
In this case, it's 8. Okay. Damn. My guess is that would have taken us a while to arrive at, so I'll just go ahead and tell you, although the reading already did. The expectation of a discrete random variable x is defined as the summation over all the elements of omega, the value of x multiplied by its probability. Those added up together are the definition of expectation of a discrete random variable, and the expectation is such an important concept that it has its own Greek letter, lowercase mu.
Isn't that usually the population mean?
Yes. So in this case, like this characterizes, these probabilities characterize a population of bowling outcomes for this bowler. So yes, we are talking about the population here, even though the distinction between population and sample is a much bigger deal from a frequentist perspective than it would be from a Bayesian perspective. But yes, this is the definition of expectation in a probability context. And like a lot of things in probability, the word doesn't mean what it means in English. So expectation in English is sort of associated with what it should happen. Like you're expected to show up at class on time or something like that. There's no like normative connotations to expectation in a probability context. It is simply the sum over the entire sample space, each element of x multiplied by its corresponding probability, add it all up together to get some number, expectation of x, typically associated with the symbol lowercase Greek letter mu. So the expectation operator takes in a probability distribution and outputs a scalar. This is not random anymore.
Right, so you want us to get these slides?
Yes, I will push them to GitHub after class today and after each class, but not before because then you could just flip ahead and see what all the answers are. But and you should have already gotten the slides from week 1 and week 2 when you hit the blue arrow. The QMD file. All right. So the expectation is a probability weighted sum of the sample space omega. And we can use whatever probabilities we want, as long as they're non-negative and they add up to 1. But exactly which values you use affects the value of the expectation. All right. So how would you compute the expectation of the first roll of a frame of bowling using the database of 10 million frames that we simulated last week and that you have sitting around in your R sessions memory?
Isn't it like something like summarize, and then you would put like the frames, data frame, comma, like mean equals x1?
So you can summarize the frames database, call mean of x1. That's technically an estimator of an expectation, but you're estimating it with 10 million values. So this is going to be extraordinarily close to the true expectation. You get a value 7.04. And then how would you do it the ancient way? Using the PR function. You feeling it?
Kind of. I don't know whether if I can get the mean part down, but I have a general idea.
Okay, let's hear it.
All right. So would you do like sample parentheses omega size equals 1 and probability like PR of like the PR of the x1?
That would be an estimator of an expectation, but anytime you're calling sample, now you're doing it the modern way with simulations.
Oh, okay.
And if you were going to do it the modern way, you'd probably want to do more than one
Okay.
in order to get a better estimator of the expectation. But the ancient way is deterministic. So no sample, but using the PR function and the definition of expectation.
Would you like move through all the probabilities using the PR function?
You could do it with a loop. Actually, it's not necessary to do it with a loop explicitly. you can just do this, which corresponds to the definition on the previous, which should memorize. So sum of each of the elements of omega multiplied by their corresponding probabilities, add it all up together to get one number, and that one number is 7.043447. There's some more decimal places, but R only shows like 6 of them. But anyway, you can take this as more or less exact. And this underscores an important point about expectations, even though it should be fairly obvious from the definition. If x is a discrete random variable, integers and whatnot, well, the probability is a real number. If you take an integer and you multiply it by a real number, you're going to get a real number. If you add up a bunch of real numbers, you're going to typically get a real number. So the expectation of a discrete random variable, in this case, 7.043447, even though never in the history of bowling has anyone knocked over 7.043447 hints. So it's not like the expectation is what you think should happen. This is literally impossible. But the expectation is a probability weighted sum of omega. And so you can think of this as the population average for this bowler in terms of the number of pins knocked down. Okay. So how would you calculate the expectation of the second roll exactly using the 11 by 11 table that we made last week and you have sitting in your R session for what the probability of all the things that could happen in a frame, 2 rolls in the same frame of bowling? How would you calculate the expectation of the second roll? Deterministically, ancient way. Could do it pretty easily the modern way, just change that x1 to x2. Expectation for the second roll, frame of bowling, not conditional on the first roll, regardless what happens on the first roll, irrespective of the first roll. Here we go.
Yeah, don't you still have to, you sum all the probabilities, well, all the, how do I say it, the scores that you could get on the second roll, right? In other words, 0 to 10, and then you have to weight each of those outcomes by the probability of getting there in the first place, right?
Yeah. In particular, it would be that. Summation, all the elements of the sample space, multiplied by the marginalized probability of knocking down that number of pins on the second roll of a frame of bowling, irrespective of the number of pins knocked down on the first roll of a frame of bowling. Remember, we did column sums to get the marginal probability of knocking down x2 pins on the second one. We did row sums to get the marginal probability of the first roll. But here we're talking about the second roll. So we do column sums. We get 11 probabilities. Multiply them by the 11 elements of omega, sum it all up, get something slightly greater than 2. Follow up?
Actually, I was going to ask, instead of giving the answer, but what is the point of doing it the modern way? I mean, does it take less computing power or?
Oh no, it takes much more computing power to simulate if you're going to simulate 10 million. It takes orders and orders and orders of magnitude more computing power to do that than to do 11 multiplications and 1 addition. 11 multiplications and 1 addition is nothing for a computer. It was even feasible 100 years ago. The reason why we are emphasizing doing things both the modern way and the ancient way is that the modern way generalizes, and the ancient way is going to stop generalizing next week, I promise. But until that moment comes, we're going to do it both ways, mostly, so that you can see that these two ways of doing things are a description of the same thing. Moreover, I think maybe it should start to be clear by now that once you have a giant database of simulations, answering questions is really rather easy. Now, it may take you a little while to get the hang of the dplyr syntax, but you can answer complicated questions with relatively simple code if you have a database of 10 million simulations of the phenomenon you're talking about. Now, obtaining those 10 million or whatever are simulations, that can be as complicated as you want it to be. And we've started off with something, like I said, relatively simple, bowling, but bowling is still rich enough to illustrate all the concepts, most of them, that we need for probability. So obtaining frames, simulations, can be complicated, but that's a question of degree. Answering the questions once you have the frames is honestly a lot easier than doing the ancient calculations. But before they could have the ability to do like 10 million simulations in less than a second, they were doing stuff with like a feather or a slide rule or whatever. So that was all deterministic calculations. Was there a question over here? Thought somebody was waving at me. Maybe not. Question over there. Question anywhere. Okay, so let's briefly turn our attention away from bowling. So the so-called Bernoulli distribution is defined over a sample space that only consists of two elements, which are conventionally denoted 0 and 1, where 1 corresponds to something that you might think of success and 0 as failure, even though it doesn't really matter which way you think about it. So in like a public health context or whatever, success often means you have the disease, which, you know, from the perspective of the person who's sick or whatever, is not really successful, but whatever. And the Bernoulli distribution depends on a probability parameter. This can be denoted different ways. I'll call it pi. So pi is a real number between 0 and 1. Probability people often use pi to denote unknown probability because it like starts with the letter P. This pi has nothing to do with the circle. Okay, it's not 3.1415. Okay, probabilities have to be between 0 and 1. The circumference of a circle is not. Circumference of a unit circle is not. And by introducing these parameters such as pi, we can make probability distributions more flexible and applicable to a wider variety of situations. So instead of just thinking about like coin flips, which, you know, if we say heads is success, tails is failure or whatever, you know, that's going to have a 0.5. But with the Bernoulli distribution, we can think about weighted coin flips. And thus it could be applicable to any coin or, you know, metaphorical coin of, you know, what's the probability you get cancer or something like that. The probability thereof, we can make it large or small for different situations, and we can make probability a function of other things, like does people in your family have a history of that cancer or that disease or whatever. Probability may be higher than it would be for somebody else.
So we can't really do, like, I know we're talking about population, but if we want to look at the subset of the population, like is it possible, like, that all of these parameters will also be the same if we're looking at a smaller subset of the
Well, they can
population?
differ from one group to the next.
Okay.
So we can certainly stratify our population into, you know, white and black, men and women, rich and poor, you know,
Okay.
all those sorts of things, in which case the probability of whatever we're talking about may be different.
Oh, okay.
So in general, when we use this, we're going to allow pi maybe to be a function of observable covariates, but that's a step beyond what I want to get to right now.
Okay.
So the probability that x equal 1 is pi. Probability that x is 0 is 1 minus pi, since there's only two events. And this can be written in the form of a probability mass function. So technically the bowling thing was a different probability mass function, but these probability mass functions are the functions that we evaluate to tell us the probability that x is whatever from within its sample space. Sample space here only consists of two elements, and in a computer we would probably do like if else, but when writing this in mathematical notation, you'll often see it written pi raised to the power x multiplied by 1 minus pi raised to the power of 1 minus x. And that works because any number raised to the power 0 is 1. And so if x is 0, we have pi to the 0, which is 1. 1 multiplied by this raised to the power 1 is just going to be 1 minus pi. And similarly, if x is 1, then this is 0, and so that becomes 1, and we're left with pi raised to the power of 1, which is pi. Okay? So you'll often see these probability mass functions involving powers of positive numbers, and those powers in the exponents can sometimes be 0, but that's okay. Okay, here we go. What is the expectation of x if x is a Bernoulli random variable?
It's just pi, isn't it?
It is. How did you arrive at that?
Oh, because you take each of the outcomes and you weight them by probabilities, but then you have 0, so then you're just left with 1 times the p, or 1 times pi.
Yeah. So technically speaking, it's 0 times something, but 0 times whatever is 0, plus 1, x equal 1, times pi to the 1, which is pi, times 1 minus pi to the 0, which is 1. So you have pi times 1, which is pi. So the expectation for Bernoulli random variable is pi. Pi is a real number between 0 and 1. So generally it's going to be strictly between 0 and 1. So the sample space here is 0 and 1. And the expectation is in between those two integers in general.
Wait, but when you include the small x, isn't that just the binomial distribution instead of the...
We're going to do binomial next.
No, but I mean, by definition, Bernoulli distribution is only for one draw, isn't it?
Right, for 1.
So why would we put what's the point of putting those exponents in the...
You could do it with if else, and that would be fine too. This is valid. I'm just showing you where the raising stuff to the power of 0 comes from. But yes, it seems like overkill to spell it all out this way. Okay. Bernoulli random variables. Next, we want to talk about the binomial distribution. So binomial random variable can be defined as the sum of n independent Bernoulli random variables that all have the same success probability. Like we talked about last time, random variable is a function. So a function of a random variable is a composite function, but it's also a random variable. So if I have n Bernoulli random variables, which are 0 and 1, and I sum them together, I'm going to get a new random variable. And that summed random variable has what is known as a binomial distribution. So then the question become, what is the sample space for a binomial random variable? Let's start with that.
It'd still just be 0 and 1.
So if I had n equals 1, that would be true. If I had n equal greater than 1,
Oh, so it'd just be between 0 to n, right?
the
The amount
integers
of times.
between 0 and n.
Any positive real integer then.
Well, yes, n can be any positive number, but we're going to condition on n, usually. And so n is fixed.
Wait, but n has to be an integer, right?
N has to be an integer, correct. We're summing n Bernoulli random variables to make a new random variable. It's called binomial. So if the sample, let's say n is 10, and so the sample space omega would be the integers between 0 and 10. Should we use the binomial distribution for the first roll of a frame of bowling?
No,
No. Why?
because there's more than 2 possible outcomes.
Well, for each pin, there's 2 possible outcomes, knocked over or not knocked over. And if we summed those,
Because they don't all have the same probability.
so that's one reason. If the pins in the middle are more likely to be knocked down than the pins on the edge, then the pins would not all have the same probability, in which case the Bernoulli or the binomial would not be applicable. What's another reason why we would be dubious of using the binomial distribution for the first roll of a frame of bowling?
Because I mean, because the size of the pin, the size of the ball hits one pin, and chances are it also hits the pins that are next to it. You know, no matter where the ball.
Right, which is a more physical way of saying the pins are not independent of each other. If one pin falls down, the pins adjacent to it are more likely to be knocked down than the pins that are not adjacent. So no, binomial distribution would not be particularly appropriate for the first roll of a frame of bowling. But if we did like survey data, and the survey asked, do you plan to vote? A whole bunch of people who have never, met each other, well, then it's more plausible to think of their sum, or think of them as independent, in which case, if they all have the same success probability, to sum them to get sort of total votes. Okay, what would be the expectation of x if x is a binomial random variable? Pi times n? Yes, that is true. So if we go back to our definition of expectation, mathematical terms, expectation is a linear operator. In less mathematical terms, you could, pull stuff out in front of the summation if it's a constant. So, let's say we're adding up n Bernoulli random variables to form a binomial random variable. Each of those Bernoulli random variables has the expectation of pi, and because we're summing a summation, since all those pi's are the same number, we can just say n times pi, and we'll get the same thing as if we did it the long way. And so the expectation of a sum is the sum of the expectations. And so in this case, the sum of the expectations would be n times pi. So the fact that the expectation of a sum is equal to the sum of the expectations is true even if the random variables are not independent. But in this case, the Bernoulli random variables are independent, but that's still fine. And so that implies in this case expectation of binomial random variable n times pi. That's in general going to be a real number. Okay? Good so far with binomials? Okay, how would we come up with an expression for the probability mass function for the probability of x given that n is equal to 3? Also conditional on the success probability pi. And as a helpful hint, there are 8 cases that need to be considered when coming up with a mathematical expression for the probability of x if n is equal to 3 and consequently the sample space is 0, 1, 2, 3. So what would be the 8 cases that comprise such an expression for the probability mass function in the binomial case if n is 3?
Is it kind of doing like the n over k, so like the 8 choose 3 basically, so you have like 3, so it's like 3 different combinations with 8 cases basically.
It is. It's not 8 choose 3, but that was on the right track. So 2 of the 8 cases, well, all 3 could succeed. And so that, since they're independent of each other, that would just be pi cubed. Or all 3 could fail, which the probability of that would be 1 minus pi cubed. So that's 2 out of 8 cases right there. Or we could have 1 success and 2 failures. So pi raised to the power 1, 1 minus pi raised to the power 2. But there's 3 ways to order 1 success and 2 failures. And the order, it doesn't really matter, but we need to account for the fact that, you know, the first one succeeding and the last 2 has the same probability as the first 2 failing and the last one succeeding. But we need to add up over those. So similarly, we have 3 cases with 2 successes, 1 failure, and 3 orders, 3 ways to order that. So that gives us our 8 cases. 2 here, 3 there, 3 there, for 8. And as was almost said, in general, a way to write the probability mass function for binomial random variable, probability of x given n and success probability pi, can be written in terms of this function, which reads as n choose x. So it would be 3 choose x, not 8 choose x. Pi raised to the power x, 1 minus pi raised to the power n minus x. And the choose function can be written slightly less concisely, but certainly more explicitly, n factorial divided by n minus x factorial divided by x factorial. Again, keeping in mind 0 factorial is defined to be 1. So this division is always going to be cool. So anyway, this is the definition here, this first term here, of the choose function. And this has the effect of adding up all the ways in with the different orderings or whatever, where you could have x successes and exactly n minus x failures in Bernoulli's.
So in this case, like 8 would be x then, right?
X would be 0, 1, 2, or 3.
Oh, okay. The reason why I was just asking was like, could you have like a negative, like if you do n minus x and get a negative result? But yeah, that makes sense.
You should not get negative numbers when dealing with probabilities. And if you did, that would suggest you haven't got your sample space right.
Okay, got it.
Questions about the binomial? All right, let's use that binomial in the context of bowling. So first, let's type this. We did this in recitation, and if you haven't seen that, the video is on Canvas under Panopto video sessions or something like that. So let's mutate frames to add another column, which indicates the game. So bowling is organized in terms of games. Games have 10 frames each. And so we want to repeat 1 to 1,000,000 10 times. So we get another integer indicating is this the first game, the second game, the third game, whatever. If we have 10 million frames, that's 1,000,000 games with 10 frames each. So we now have an indicator variable for what game are we talking about? All right. Question? Has everybody managed to type this? Okay. As you're typing that, think about how you would compute the probability of getting exactly 4 strikes in a game of bowling using your database of frames, which is now grouped into 1,000,000 games. So probability of exactly 4 strikes in a game of bowling, modern way.
What package is the mutate function in?
Dplyr, but that should have been loaded up already when you did source bowling.r. Probability, exactly 4 strikes, game of bowling, modern way. All right, so like I said, this is fairly easy once you have your simulations, but it takes maybe a little bit of practice to get the hang of the dplyr syntax for something like this. So we want to group by the game variable. So we want to do this for each of the 1,000,000 games. Pipe that to the summarize function. Define a new variable, 4 strikes, which is true if the sum of the number of frames where x wanted 10 is exactly 4. So we want to define for each game, new variable called 4 strikes. We get the logical vector of size 10 here is x1 equal to 10. We add those up. If the number of strikes in the game is 4, we get a yes. If the number of strikes is not 4, we get a no. Question?
Yeah, I was gonna ask, like, I was thinking of multiplying it, so that wouldn't make sense then. In this case. Okay.
Not the modern way.
Okay.
Ancient way often entails a multiplication.
Got it. Okay.
But anyway, so this, when you group by, summarize, and then groups is drop, now we're going to get a data frame or a tibble with 1,000,000 rows. And 1 column, or 2 columns, one is the game, the other is this new column called 4 strikes, which is either going to be true if that game had exactly 4 strikes, or false if that game had any other than 4 strikes. Then we're going to pipe that to another summarize where we calculate the proportion of times that a game resulted in 4 strikes exactly. And that number comes out to be about 0.18. All right. So in this case, the syntax for it, I would admit, is a little bit more challenging than what we've done previously, but it's still qualitatively the same thing. What do you need to condition on? That'd be a filter, or if you want to do it for everything, that'd be a group by corresponding to a for each. And then it's a lot of, sum and summarize and take the proportion and stuff like that. End up with a 0.18 probability of a game of bowling for this bowler having exactly 4 strikes. Okay. So, yeah, you didn't see that. How would you calculate it the ancient way using the binomial probability mass function?
Yes, you would use the formula, the really long formula that you showed. So you would do,
That one?
in this case, n would be 10, and then x would be 4, and then the probability would be 0.179, I think to the 4, and then it would be 1 minus the 0.179, 10 minus 4, and then you set it equal to the, I'm looking at my notes, the n factorial, so that would be 10 factorial over 10 minus 4 factorial times 4 factorial, and then 0.179 raised to the 4th, and then 1 minus 0.179, 10 minus 4, which is 6.
Yeah, that's the right idea, even if you didn't catch all that. There's one mistake. So what's the probability of success that we need to be used here? It's not 0.179. It's
It'd be, in this case, 0.0537, whatever your probability of rolling a 4 is based off the probability max from that you give.
okay, so what's the success here in this context?
You get a 4.
4 strikes.
4 strikes.
Success is a strike.
Oh, 4. Oh.
So the thing we need to use for pi is the probability of a strike, which is like 0.28. Yeah, for us.
I thought it was 4 pins. Okay, I was thinking about
No, not 4 pins, 4 strikes. So the way in which you can calculate this more easily than whatever is in your notes, choose 10, 4, success probability raised to the power 4, failure probability raised to the power 6 for the probability of exactly 4 strikes and 6 non-strikes. Considerably easier than what was said there. But even easier, binomial probability mass function is built into R, like a lot of other probability distributions. These have the convention starting with the prefix D and then ending with some abbreviation of the probability distribution. So D binom is the probability mass function for a binomial random variable, aka this. And 1, it's already in R, and 2, it's going to be more accurate in general for like all possible things that you could give it. So you want the probability of 4 successes in 10 tries, n equal 10, but it's called size rather than n. And then the success probability for each of those 10 events is, in this case, the probability of a strike using our bowling function. Get literally same number, which is essentially what we got the modern way from the simulations. Questions? So you certainly can and really should use the built-in functions for R when they're available to you. That's fine. So like memorizing a bunch of formulas like this, not essential, although you should probably remember it well enough to recognize it if you see it again. But it's built into R. There's no shame in doing it this way here. Questions? All right, here we go. Poisson for counts. So let's think of a binomial, but let n go to infinity. Now, if pi is fixed and n goes to infinity, then the expectation would be infinity. Not super interesting. So to make this be a little bit more interesting, but perhaps a bit contrived, we're going to let n go to infinity at the same rate that we let pi go to 0, which is to say mu, the expectation of the binomial, which is n times pi, remains fixed as n gets big and pi gets small. So n is increasing at exactly the same rate that pi is decreasing, so that mu is a constant that is fixed. And if that's the case, then pi is going to be mu divided by n. So that's getting small as n gets large. And then the question we want to ask, or Poisson did ask, what is the limit of the binomial PMF, replacing pi with mu over n under those assumptions? And so I'll just quickly walk through this. It's not super important for a class like 5065 to know these derivations. But I'll just put one up so you can get a sense for like how this came about. So if we think about the first term, n choose x multiplied by pi raised to the power x. If pi, we substitute that mu over n. So we get this. Rearrange it a little bit. We're going to get n to the x in the denominator. And we're going to get x terms involving n in the numerator. So as n goes to infinity, that is going to approach 1, leaving us with mu raised to the power x divided by x factorial. And now if we look at the other term, 1 minus pi raised to the power n minus x, again substituting mu over n for pi, we get this. We can break it out into two terms, 1 minus mu divided by n raised to the power n. And maybe a little known fact among QMSS students, but that is the definition as n goes to infinity of e, the number 2.718-ish, raised to the power negative mu. That's one way to define e. And then this piece over here, well, x is fixed, so 1 minus mu over n is going to 0. We have 0 raised to the power, or we have 1 raised to the power negative x, which is going to be 1. So this becomes e to the negative mu. Put it all together, the limit of this process as n goes to infinity, if pi is defined as mu over n, is the probability mass function given here, mu to the x from this, e to the negative mu from this, x factorial in the denominator, which is the probability mass function of the so-called Poisson distribution, and it is going to be defined over a sample space consisting of all non-negative integers. So this is the first time we've encountered a sample space that does not have a finite number of elements, has a countable, in this case, infinite number of elements. But we can evaluate this function for any non-negative integer in principle. And the expectation of the Poisson distribution is mu. So Poisson arises as a particular limiting case of binomial when you have a large or maybe infinite number of trials. And the success probability of each of those trials is fairly small. So Bernoulli, binomial, and Poisson are three of the most basic discrete probability distributions. And they involve an unknown parameter, which ordinarily in statistics we would be trying to estimate. So a lot of statistics, particularly a lot of statistics 100 years ago, was about estimating the expectation from data that is assumed to be drawn from some distribution, binomial, Poisson, whatever. Questions? Bernoulli, binomial, Poisson? Again, you don't really need to know the details of how the Poisson arrives or can be motivated as a limiting case of binomial, but just, that's one way of defining it, or one way of motivating this expression, and this expression is a valid probability mass function. It yields numbers that are non-negative, and they sum to 1 over the entire sample space, but the sample space in this case is all non-negative integers. So that would be an infinite sum, but the infinite sum of this probability mass function converges to 1 if you sum it from 0, x equals 0 to x equal infinite.
Sorry, I don't think I understand the last statement, like the 0 to z.
Oh, z plus, that's a math convention for positive integers.
Okay.
So the sample space for a Poisson random variable is 0 and the positive integers, which is to say the non-negative integers. So 0 is valid, and as is any other positive integer, but not negative integers and not real numbers.
So the main purpose of doing this is to like find what the limit is to like having a sample size, basically.
Yeah, so if you had a situation in which you're counting up successes,
Okay.
but there's no upper limit to the number of trials, or
I
no
see.
known upper limit to the number of trials, the Poisson may be applicable. Honestly, there's probably better choices than Poisson.
Okay.
But this is something, because it follows from the binomial, it's considered among the 3 most basic ones. So we're talking about it today because it's basic, not because it's universally applicable. But it's more complicated than binomial or Bernoulli, but less complicated than what we'll do next week when we get to continuous random variables. Other questions before we move on?
Sorry, just another follow-up. Is this applicable only for binomial distributions then, like this
So
specific group?
binomial with unlimited n.
Okay. Just want to make sure. Thanks.
It's likely like time, maybe.
If time is measured in discrete, like days, but if time is measured in milliseconds, then
In Bayesian statistics, do we ever concern ourselves with the variance of these estimators that are distributed, like this?
well, we wouldn't concern ourselves with the variance of a point estimator. We will concern ourselves with the variance of the posterior distribution.
I see.
But let's get to a posterior distribution before we worry about its variance. So that brings me back to bowling, as if I ever left. So let's do this example. It's a little bit artificial because we usually almost always think about parameters as continuous random variables. And we're going to get into that next week. Here, I'm going to introduce a discrete parameter. It can only take non-negative values. So this is admissible. It's an example of the process of using Bayes' rule. But it's not something that I would ever actually do. But I could do it. So let's let the probability of knocking down x out of n pins also depend on an unknown parameter kappa, where kappa is a non-negative integer. And the way in which our probability mass function changes is now we're taking the logarithm to base n plus 2 plus kappa. And in the denominator there we have n plus 1 plus kappa minus x. And then we're going to divide by 1 minus the logarithm to base n plus 2 plus kappa of 1 plus kappa. And so that seems like a weird formula. But if kappa is 0, the logarithm of 1 is 0, so 1 minus 0 is just 1. And if kappa is 0, we get back exactly the probability mass function that we were using last time. So when we did the first roll of a frame of bowling last week, it was only conditional on n being 10, which is like according to the rules of bowling. But n is known. Okay? Now what's changed, the probability for the first roll of a frame of bowling depends not only on n equal 10, but the kappa of the bowler. And if kappa is 0, we get exactly the same probabilities as we had before. So you can think of last week as a special case of this where kappa is 0. But kappa doesn't have to be 0. Kappa can be any non-negative integer. So if kappa is 1, then the probabilities are like this, with the probability of a strike being a little bit lower. If the kappa is 9, then the probabilities are this. The good outcomes are getting, lower probability than before, and the bad outcomes are getting higher probability than before. And so we can think of kappa as an inability parameter that each bowler has that governs their probabilities. But the probabilities are still, for any integer, non-negative integer value of kappa, these probabilities are non-negative. And if you added them all up across the rows, they sum to 1. So they're admissible. But they change depending on the value of kappa. Higher value of kappa, lower probability of a strike, higher probability of a gutter ball, but also the intermediate ones change. All right. So last week was a special case where kappa is 0. Now we want to think about the general case, more general case. So how would you calculate the expectation of the first roll given that kappa is 2? And you might have noticed that the probability in the bowling.r, the PR function that we have now has 3 arguments, x, n, and kappa. But kappa defaults to 0. So if you call it with the default values, you get the same thing as last week. But you can call it with any non-negative integer for kappa. So how would we calculate, using ancient ways, the expectation of the first roll of a frame of bowling given that kappa is 2? Using the PR function that God defined when you did sourcebowling.r this week. So how do we calculate those expectations? Ancient way. What's it start with? Sum. What goes in the sum? Omega times the probability. And so we get the probabilities in this case by evaluating our PR function at omega, n equal 10, because this is the first roll, and we're conditioning on kappa equal 2, which is going to be somewhere, the probabilities are going to be somewhere between for 1 and for 9, whatever they are. They add up to 1 and they're non-negative, so they're totally admissible. So now we get an expectation for the first roll, given that kappa is 2, of 6.35-ish, less than the 7 point something that we had when kappa was 0. So if you use conditional probabilities to form your expectation, you get a conditional expectation. If you use marginal probabilities, you get a marginal expectation. You use joint probabilities of a function involving 2 or more variables, you can get a bivariate expectation, etc. So the process is the same, but which probabilities you use depends on what question is being asked of you, or what question you are asking yourself. All right. So by changing kappa, we can change the expectation of a first roll of a frame of bowling. And as it happens, the expectation is a monotonically decreasing function of kappa plotted here. So if kappa is 0, the expectation of the first roll of a frame of bowling, slightly above 7. For kappa equal 1, kappa equal 2, 0, 1, 2, all the way down. And then as you get bigger values of kappa, the expectation for the first roll of a frame of bowling approaches 5 because the probabilities approach 1/11th for all 11 possible events in the first roll of a frame of bowling. So if we're thinking in terms of what would be a prior on kappa, you can start by saying, well, what do I think the expectation of the first roll of a frame of bowling for this bowler is? Start over here, find the dot closest to that vertically, and then down to the horizontal axis here, get a corresponding value of kappa that would imply such an expectation for the first roll of a frame of bowling. And so my question for you is, what expectation would you choose for yourself in a Poisson prior over kappa? Using that process, starting where you think, how many pins could I average on the first roll of a frame of bowling, over to the dots and down, what value of kappa would that be for you? No right answer. But another way of saying this, with the introduction of the kappa parameter, we could make our bowling thing applicable not just for the one bowler that we were talking about last week, but for any bowler who would average between 7 and 5 pins knocked down on their first roll of a frame of bowling. It doesn't have the flexibility to get up to professional bowlers who would average much closer to 10. It doesn't have the flexibility to go down to your average 8-year-old at a birthday party whose expectation is much less than 5. But it has some flexibility, at least for people whose average is between 7 and 5. Question over here.
No, I was about to ask about what you're talking about, applicability to more professional people.
Yeah, this would not be great for professional bowlers. Doesn't have enough flexibility yet. But it has more flexibility than what we had last week. And that's a good thing. All right. So let's say expected value of kappa for some bowler, let's call it 8.5. And so they're going to average, 5 2/3, something like that, first roll. Okay, so now how would we simulate our frames of bowling along with kappa? So let's type this one with me as I explain it. So first we're going to set R to some huge number like 10 to the 7th. Doesn't really need to be that big, but big enough to where for all practical purposes it's infinite, even though we can't literally do an infinite number on a finite computer. We're going to set M equal to 8.5. That's the expectation of our Poisson prior on kappa. And then we're going to create a tibble called frames with 10.7 or 10 to the 7th rows and 3 columns. Those 3 columns are going to be kappa, x1, and x2. So compared to what we did last time and in simulations, now we're going to have a third random variable that we're simulating kappa, because the conditional probabilities for the first roll and the second roll are both going to depend on kappa. So we're going to start by drawing kappa from its Poisson distribution. So by convention in R, lowercase r suffix, prefix, followed by abbreviation of the distribution suffix, is the convention for the function that draws random values from that distribution. Now we used sample for this before, but sample only works if the sample space has a finite number of elements. So we can't put sample 0:infinity, because it's a finite computer. But so there's a special, not that special, but built-in function for R for drawing from a Poisson distribution called RPOIS. So we want to take R draws from the Poisson distribution, and the expectation of the Poisson distribution is M, which we set to be 8.5 to indicate this bowler is not really very good. Okay. With me so far? So at this point, I have a tibble with one column and R rows. And the first column is called kappa. It has realizations from my Poisson prior on kappa. Now I'm going to group by all the unique values of kappa. And for each value of kappa, I'm going to mutate another column called capital X1 and call the sample function, much like we did before. Omega is the sample space. Size is in parentheses, so this function evaluates how many rows there are for each group of defined by the unique values of kappa. We're going to sample with replacement, which is to say the 10 pins get set upright every frame. And the probability of knocking down that number of pins is probability of omega, n equal 10. But now we're going to condition on the value of kappa, all right? Or the realization of kappa that we got from line 4. So this is going to create a second column, and it's going to do it for each unique value of kappa. It's going to create a second column called X1, which is going to have integers between 0 and 10. Then I drew sample, much like last week, except now X1 is conditional on kappa. Now I'm going to group by both kappa and X1, so the intersection of kappa and X1, however many unique combinations of that. I'm going to do this for each of them. I'm going to mutate a third column called capital X2, where I'm going to sample the second roll for each of these frames of bowling. Sample from omega, size is whatever, replace is true, and then the probability is omega 10, n is equal to 10 minus the realization of x1, and I'm going to continue to condition on the realization of kappa. When I ungroup that, I'm going to have a tibble with R rows, 3 columns. The first column is going to have my realizations of kappa from a Poisson distribution. That can be any non-negative integer, but they're going to have an expectation of 8.5. And then there's going to be x1, which is pins. So it's going to be numbers between 0 and 10. Then it's going to have another column x2, which is also pins, but x1 and x2 together can't be greater than 10. So it would look a little something like this. Yours is going to be randomly different, but it's going to have the same structure. So the first row I got a realization of kappa of 8. 7 pins knocked down on the first roll of a frame of bowling for this person with the kappa of 8, and 3 pins knocked down on the second roll of a frame of bowling. Other of my R rows here involve different values of kappa, but the values of kappa have an expectation of 8.5 under my prior, and both x1 and x2 are conditional on the corresponding realization of kappa. In addition, x2 is conditional on x1 because n is equal to 10 minus x1 when the last column got simulated.
I'm kind of confused with like what's the purpose of the x2 column? Is that just like its own separate game of bowling? Because I know
No, it's the second roll of a frame.
Oh, okay.
So each of these are, the first frame here is 7 and 3.
Oh.
Second frame is 6 and 0. All of these added together, they're going to be no greater than 10.
Oh, okay, got it.
So if you didn't see this part, we have what we had last week.
Got it.
But
Okay.
in reality, these realizations are conditional on kappa, and so we need another column for my realizations of kappa from my Poisson prior distribution. Not a question? Question?
Sure, so kappa is just there to serve to change the Poisson distribution, so each different frame just has a different distribution, so different
Right.
probability.
And over 10 million, this sort of represents our beliefs about a bowler whose expectation of their Poisson is 8.5, what their data is anticipated to look like. Right. So before we had 2 columns, now we have 3 columns. And now we have 3 random variables, kappa, x1, and x2. And this is the more Bayesian version of what we did last week, because it involves simulating kappa, which according to frequentist, kappa is not a random variable. So why are you drawing it from a Poisson? Kappa may be unknown, but it's a fixed scalar. It's not being randomized by any process. From a Bayesian perspective, we're saying, okay, this is my beliefs about the unknown kappa are described by a Poisson distribution with an expectation of 8.5. So I can have beliefs about somebody's kappa, whether it's my own or someone else's, and I'm going to describe my beliefs with a probability distribution. The same way I can say my beliefs as to whether that number x1 plus 10 to the 100,000, I can have beliefs about whether it's a prime number or a composite number, and those beliefs can change as I get more information about it. Okay, so you don't have to copy this down, but I'm going to walk through it, how I would make trivariate probabilities the ancient way. So first I'm going to create a 3-dimensional array that's 40 by 11 by 11. You can think of this as a stack of 40 matrices, each of which is 11 by 11, and the 11 by 11 matrices contain in them the joint probability of knocking down x1 pins in the row and x2 pins on the column. But I'm going to stack up 40 of these for 40 different values of kappa. And even though kappa can be any non-negative integer, 39 is practically infinite if the expectation is only 8.5. So the probability under a Poisson prior with expectation of 8.5 of 40 or greater than 40 is so small that I don't even have to worry about it on a computer. It's going to be some number that's slightly greater than 0, but it's going to be like 10 to the negative 20th or something ridiculously small like that. So I'm going to loop over the possible values of kappa between 0 and 39, and I'm going to evaluate the Poisson probability mass function, which is the d Poisson function, evaluate that at kappa with expectation in. So that's going to be a number, a probability between 0 and 1. And then I'm going to loop over the sample space for my first roll of a frame of bowling, calculate the probability of knocking down x1 pins, given that 10 are up, and I'm conditioning on kappa. I can multiply probability of kappa times probability of x1 to get the bivariate probability that kappa is whatever and x1 is whatever for all ish values of kappa and all values of omega. And then I'm going to loop again from 0 to 10 minus x1. I have to plus 1 the indices again because R starts numbering with 1, not 0. And I'm going to fill in the corresponding element of my 3-dimensional array called trivariate PR with the probability that kappa is whatever and x1 is that, both together, times the conditional probability of knocking down x2 pins on the second roll of my frame of bowling, given that 10 minus x1 pins are upright and conditional on the value of kappa which governs the probabilities for how good or bad this bowler is. So at the conclusion of all three of those loops, I have a 40 by 11 by 11 structure. And if I sum those all up, I get 1, or arbitrarily close to 1, because I did this correctly. And so now we can think about the relative values of each of these. And so the apply function is very useful in R, but you may not have seen it before. So the apply function takes an array, which would be like a matrix if it only had 2 dimensions, or a vector if it only had 1 dimension. This has 3. And it applies whatever function you say to whatever margins you indicate. And so by saying I want to sum across the first 2 margins, so margin here you can think of as, say, include or keep the first and second margin. First margin corresponds to kappa, second margin corresponds to x1, but I'm going to sum it over the values of x2. So I'm marginalizing away out x2, and that leaves me with a table for the bivariate probability of kappa and x1 together if m is 8.5. And so these are the possible values for number of pins knocked down on the first row, and these are the values of kappa. You can see here this goes to 11, but that's just however many I could fit on this slide. It actually goes to 40, and conceptually it goes to infinity. But past 40 it's so small that you don't even really need to worry about it. So the probability that kappa is 7 and 8 pins are knocked down on the first row of a frame of bowling is 0.015, etc. And as we saw before, if we sum over all 3, we get 1. But now we're just summing over the third, so we get this 40 by 11 structure here for the bivariate probability of kappa and x1. Pins knocked down, first roll, frame of bowling. So how will we do modern way? Obtain the probability that x1 is 8, irrespective of kappa, but given that m is 8.5. So the probability of knocking down 8 pins, first roll, frame of bowling, irrespective of kappa, but conditional on m being 8.5 is what we used to generate those frames. How can we use dplyr syntax to answer that question?
Summarize frames, comma, n equals 10, comma, prob equals mean, parentheses 8, or x1 equals
X1
8.
equals 8. Yeah, so that you don't really have to do the n. It already assumed
Okay, never mind.
that there was 10 pins available to be knocked down on the first roll of a frame of bowling. So yeah, it's just average the proportion of times where x1 is 8. And to marginalize in a modern context, you just don't mention the stuff that you're not conditioning on. There is no filter. So this is an unconditional probability that x1 is 8. Comes out to be about 0.109. And so then how would we do the ancient way? Calculate the marginal probability of x1 being whatever, irrespective of kappa, irrespective of x2, using our trivariate PR structure, which has 40 rows corresponding to the possible values of kappa, 11 columns, and 11 things that are beyond columns. They don't really have a word for the third dimension, except the third dimension. So how would we calculate the marginalized probability of knocking down x1 pins, first roll frame of bowling, irrespective of kappa, irrespective of x2, ancient way, deterministic way? way using the apply function that we just learned about. Maybe need to see another example to learn about it a little bit more. So marginalized probability of stuff, first roll, apply to our trivariate PR function. If you do negative numbers, that means marginalize out the first and the third margin. So I could have just said 2. Positive numbers means include, negative numbers means exclude. So excluding the first and third dimensions, summing over them, I get these numbers here, in which the probability of knocking down 8 pins, irrespective of kappa, irrespective of x2, is 0.1089, corresponding quite well to the modern way we did it with simulations. We can also do it by summation with joint probabilities, trivariate probabilities, summing to marginalize over the stuff we don't want to condition on. Yeah? Yeah. And we get the same answer. All right, Bayes' rule time. How would you compute the probability that kappa is 3 given that x1 is 8 using the database of frames, but not conditional on x2? So you just observe the first roll of the first frame. It turns out to be 8. Nothing else. What is the posterior probability that kappa is 3 if the Poisson prior you used to generate the frames had an expectation of 8.5? How would you use your database of frames to answer that question? Conditional probability kappa is 3 given that x1 is 8 irrespective of x2.
I know the formula, but not the code. Is that okay?
Nope.
Okay, dang it.
Modern way, you got to know the code.
Ugh.
That's what makes it modern, in addition to it being random. Yeah?
We just filter where x1 equals to 8,
Yes?
and then summarize by the mean when kappa equals 3.
Yeah? Filter to condition. Condition on the event x1 is 8. Then calculate the probability is the proportion of times where kappa is 3. You get 0.0224. Posterior probability that kappa is 3. Updated from your prior, because you've observed the event, the data, x1 is 8. Or you've observed one data point, x1 is 8. And I could do this not just for kappa equals 3, but for kappa equals whatever, by filtering x1 equal 8, and then, making a plot of the proportions that I see, and my plot got lost because I got signed out of my own office. Re-render. Right? So in modern dplyr syntax, whatever, conditioning corresponds to a filter if you want to do it for like a particular number, or if you want to do it for all possible numbers, a group by, and then whatever you're doing. And so I don't have to restrict myself to considering the probability that kappa is 3 given that x1 is 8. I can do this with a plot based on this code, conditional on x1 equal 8, for pretty much all the values of kappa look like this. And honestly, given that x1 is equal to 8, that pretty much rules out the possibility, basically, for all intents and purposes, that kappa is 30 to 40. Any in there? the fact that you got an 8 is sufficient indication that you're like not so bad at bowling. That we can rule out some of the higher values of kappa. We're left with this, the heights of these bars, they all add up to 1. Conditional probability of each value of kappa given that x1 is 8. Okay. Modern way. Ancient way. To do that, we first need to define an 11 by 11 matrix by applying the sum function to trivariate PR, including the second and third margin, summing over the first margin. First margin is kappa. So when we get this, we're left with an 11 by 11 matrix, then marginalized over, out, kappa, and left with these joint probabilities of this or that happening on a frame of bowling, irrespective of kappa. And so when we did this last week, this number down in the bottom right for the strike probability was 0.028 almost. But that was conditional on kappa being 0. Marginalized over kappa, the probability of a strike is half as much. And these other numbers that used to be smaller are now correspondingly bigger. Still adds up to 1, but we've rearranged the probabilities because the marginalizing over kappa corresponds to a worse bowler than kappa equals 0, which is the best possible bowler under our model. But if we make this frame PR, that's 11 by 11 and marginalized over kappa. So this has the same structure as joint PR from last week, but joint PR was conditional on kappa equals 0. This one here, marginalized over all the possible values of kappa, weighted by a Poisson prior with expectation 8.5. All right. One more Bayes rule. How would you compute the probability? Kappa is 3, given a Poisson prior with expectation 8.5, and given that x1 is 8 and x2 is 2, using frames. Let's get somebody from the middle, since we're almost out of time. You're not close enough to the middle. Talking about like here. How would you use modern way probability kappa is 3, given Poisson prior with expectation of 8.5, and you observe one frame of data. First roll is 8, second roll is 2. What's the posterior probability that kappa is 3 with a database query to your 10 million frames? It's very similar to the case where we just did, where we only conditioned on x1 being 8. Now we're conditioning on x1 being 8, and the second roll of the first frame of bowling is 2.
You have the filter frames x1 equals 8, x2, and x2 equals 2, and then you have summarize prob equals mean kappa equals 3.
Yes. Filter according to 2 conditions among that subset of your database where x1 was 8 and x2 was 2. Among that, the proportion where kappa is 3. Posterior probability. It's 0.0241, which is slightly different from 0.022. Conditioning on that second roll updated your probabilities a little bit more. And then how would you calculate this posterior probability exactly, deterministically, ancient way, using the trivariate PR structure and the frame PR matrix we obtained by marginalizing over kappa in the trivariate PR structure? Ancient. Somebody in the back. Back row. Ancient calculations. Posterior PR. probability, kappa is 3, m is 8.5, x1 is 8, x2 is 2. Posterior probability is what? Using deterministic ancient calculations. Nobody in the back.
Could you go back to those functions? I think no.
Okay, so trivariate PR was defined with this triple loop business. And then bivariate or frame PR was obtained by marginalizing over kappa to get an 11 by 11, like this. And we want to get posterior probability. Okay, I guess the back row only does modern. Somebody else, since they're running a bit low on time, want to give me the ancient way? Using Bayes' rule? This is a Bayesian class. Modern Bayesian class. But we want to know how to do it the ancient way when the ancient way is feasible, which it is in this case, in principle. Using Bayes' rule. All right, we're not leaving until we get this.
Can you go back to them again?
Yeah.
Okay. Trivariate PR I made with this triple loop. I did all essentially values of kappa, all values of x1, all values of x2. The x1 and x2 are 11 by 11 matrices, and I stack up 40 of them. So I have like a tower that's trivariate PR. And they add up to 1, because I did this right. And then I made the marginal probability of a frame by marginalizing over kappa, and I got frame PR. So irrespective of kappa, I'm left with an 11 by 11. So this is the probability of all the things that could happen on one frame of bowling, irrespective of kappa, under a Poisson prior for kappa with an expectation of 8.5. All right? So we want to use Bayes' rule. It's going to have a numerator and a denominator.
Do the sum joint PR function. Or
So it doesn't use joint PR from last time because joint PR was conditional on kappa equals 0.
got it.
Now we're talking about kappa equals 3. But it's a similar process to what we did last week. Similar in the sense that fractions have numerators and denominators. So we got two things here, and we got a numerator and a denominator. So which thing goes in the numerator and which thing goes in the denominator?
Joint probability of, not in the sense of the code, but just the probability of x1 and x2 occurring given your kappa equals 3.
We want it the other way around. So the probability that kappa is 3 given the frame of data we observed.
Okay. Is it still the code or the formula now?
Code, but code deterministic.
Okay. For the trivariate PR, I got like apply. Wouldn't it be like apply trivariate, and then would you do like the similar things like kappa equals 3, and then x1 equals 8, x2 equals 2, and then fun equals sum?
So if you do trivariate PR at 3 for kappa, 8 for x1, and 2 for x2, that's just going to pluck out one number.
Okay.
So there's nothing to sum over, although if you did sum it, you would just get that one number. But that one number is the numerator that we're looking for here. The joint probability that kappa is 3, x1 is 8, and x2 is 2. And now we need to divide by the event we're conditioning on, which is
x1 equals to 8, x2 equals to 2.
a frame with 8 on the first roll and 2 on the second. And so how would we put the denominator using frame PR? Which is this. Trivariate in the numerator, kappa 3, x1 8, x2 2, divided by 8 2 in the denominator, irrespective of kappa, we get 0.0241771. Which is what we got. Modern way from the frames. Sort of the same thing. Two different ways of getting it. All right, so now we're at overtime. But we'll have more practice on that in recitation at some point next week. And do you have questions?